Hello class. So, as you know, the cache memory is becoming something very important in every computer. That's why I chose to talk about this subject, cache memory, and especially its organization, its levels, and finally we will talk about mainly the hit and miss concepts. And then we'll have a small bonus at the end of this video, so stay tuned. Let's start first about talking about cache memory. As we can notice, we can have a computer by simply having a CPU and a hard drive connected to each other. But then we will be constrained by the slow speed of the hard drive and will not make use of the fast processing speed of the CPU. And that's why we use RAM. CPU at first came without cache, as we can see in this picture. The cache memory first appeared in the 80s. It was firstly made as an external hardware, simply as the RAM. RAM speed is not enough either for the processor, so we use the cache memory, which is faster and nearest to the CPU. The cache memory is having less than the RAM memory. There are three levels of cache. The first level, which is nearest the CPU, or sometimes found in some of the cores of the CPU, and then we'll have the level 2 cache, which is faster than level 3, which can be found. So the levels are level 1, level 2, and level 3. Level 1 is the fastest as it is the nearest the CPU or inside the CPU. Level 2, which is slower than the level 1 cache. And then we have, as we can see here, the level 3. Level 3 isn't in all the cache memories, but it can be found in some of them. Cache stores components of RAM that are needed constantly. So the processor checks if what it needs is in the memory. If yes, as we can see here, is then retrieved from cache. If not, it is retrieved first from the RAM from here and placed afterwards in the cache. The cache memory tries to predict what the processor needs to run faster. As like we can say that the apps that are running for the first time are slower because of those concepts, because it needs to be retrieved from the drive and then given to the RAM and then the RAM to the cache. That's why it takes a lot of time. We can measure the cache capacity by something called the heat ratio. For example, if the CPU find what it needed for the upcoming operation, it is called a hit. A hit that we are gonna detail it afterwards in the third part of this video. If the CPU doesn't find what it needs in the first level of cache memory, it will then fetch in the second and third levels still faster than fetching directly in the RAM. Let's now move and talk about the different levels of the cache memory. So let's first talk about the fastest amongst them, which is the level 1, which we can say L12. Let's start first by talking about the level 1, which is split into two parts. The level 1 data D and the level 1 I, which is meant to level 1 instructions. Level 2 is cache memory for L1. L1 is known to be faster. It is inside of the CPU cores. That's why it is so fast. It can process the information and give it to the CPU very fast. The level 2, as we say, is a cache memory for L1. And then in some of the cache memories, we can find also level 3, which is the slowest among them, but it is shared among them. Shared cache, as we can see here, was called by Intel Smart Cache. So the last level of cache can be shared with all cores, and the cores needing the most memory will get it. It is firstly showed up in the 2006 Core Duo, which announced the start of this technology. That's all about the cache memory organization and the different levels of cache. Now, after we finish discussing the cache organization and discussing the different levels of cache, we will move now to discussing the hit and miss concepts because they are very important concepts in knowing the cache memory. So, and then we'll talk about the small bonus as we said. So now let's move to the last point, which is about the hit and miss concepts. So before jumping to cache miss and hit, that is mainly based on speculations, we'll first talk about two concepts. First of all, the closely related data, also called spatial locality, and frequently used data, also called the temporal locality, because we will use them to explain the hit and miss. So let's to better understand those two concepts, let's have two real life examples. So for the temporal locality, for example, when packing the bag, we will use a pen and a textbook. So we will pack a pen and a textbook. Why? Because they are frequently used items. So we will be picking them up. The programming example for this temporal locality can be a for loop because the counter is called again and again. So replacing it in the cache is following the logic of temporal locality. Now let's move to the spatial locality. So a real life example to this concept can be, for example, if our professor asked for a computer architecture textbook, but doesn't know which textbook he means. So we will go and search all the potential textbooks that can match and can be used, and we will pick them up all, and the percentage of their use is like equal. We can use them all at the same moment. So the programming example that I can give for the spatial locality can be like the sequential program, when instructions will go to cache memory one after one. Now let's move to talking about the hit and miss. So by talking about hit and miss, our main goal is minimizing the access memory time, which is the time taken by the processor to access the data. In order to minimize this quantity, the data must be instantly available. Here comes the term hit and miss, where we mean by cache hit successful access to the data. Cache miss means unsuccessful access to the data. Those two terms should be differentiated between them and between page hit and page miss. The page hit and page miss are mainly related to the main memory, not to the cache memory. So related concepts to those hit and miss, the hit rate is the number of hits divided by the number of attempts, and the miss rate is 1 minus h, or number of misses over the number of total attempts. So what happens if there is a miss? So when the CPU makes a request, it checks into cache. If it's available, and it is then a hit. If it is not, then it is a miss, and the CPU has to search in the main memory. If it's available, then it is a page hit. If not, it is a page miss. So the CPU will search then in the auxiliary memory. When the request is raised, data must be fetched at different levels: cache, then main memory, then auxiliary memory. To know more about that, we can say that like recent systems have the ability to directly access main memory as well. So the process goes in a parallel way rather than a hierarchical way. So when cache miss happens, it has to go search in the main memory, and there happens a delay. If it is not found in the main memory, it has to check the auxiliary memory, and that's an extra delay. This delay is called as a miss penalty, which is the extra time to bring data from one level to another. Simultaneous access, which is the access time to cache or level 1, is T1, for example. It is faster, as we can see here, than T2, but the access is during the same time. So when a miss happens, the miss penalty, as we can see here, will be T2 in this case. Now let's move to the hierarchical way, or the hierarchical access. It will take like T1 to access the cache, then it can't find it. So it is, if it can find it, it is a hit. If not, it has to access level 2. So if it has to access level 2, it has to wait for the whole process in T1, and then it will move to the searching in the main memory. So as we can see here, this process will take us T1 plus T2, access time of cache, and then access time of memory. To further understand that, for example, we can take a third level, like the auxiliary memory. So if it can't be found in the in either cache or main memory, we will have to fetch it in the auxiliary memory. So the needed time will be T1 plus T2 plus T3. So to know more about those hit and miss concepts, blocks are transferred from main memory to cache, and wherever the CPU looks for a certain data, it will look for it in the cache memory first, and if the data is found in the cache, then it will be called a hit. Otherwise, it will go through all the blocks inside the cache, and whenever it is not found in a block, that's a mismatch. It's not a miss, because we are still in the blocks inside the cache memory. But when all the blocks are went through and nothing is found, it is called a miss. That's what we mean by the hit and miss. Let's move to the bonus that I talked about in the beginning of the video. So the bonus is as follows. I will show you how to calculate the average access time of a CPU. So the formula is as follows. The formula of average access time equals the hit rate, times the time taken to access memory in case of a hit, plus the miss rate times time taken to access memory in case of a miss. As I said previously in the video, the miss rate, as you can see here, can be written as the 1 minus hit rate, because it's the same thing. So for example, we can calculate to apply the formula. The read request time needed by the CPU is 100 nanoseconds on a miss, at 10 nanoseconds during a hit. It was observed that 80% of the processor's read requests was a hit. What's the average read access time? So let's first extract the needed information. Here we have the time taken to access memory in case of a miss is 100 nanoseconds, and the time taken to access memory in case of a hit is 10 nanoseconds. As you can see, it's less, because when there is a miss, there is a penalty. When there is a direct hit, it is much faster. And it was observed that 80% of the processor's read request was a hit. So let's calculate that. The hit rate is 80%, which is 0.8 times the time taken to access memory, which is 10 nanoseconds. 0.8 times 10 nanoseconds plus the miss rate, which is 1 minus 0.8, which is 0.2 times time taken to access memory in case of a miss, which is 100 nanoseconds. So this results in 8 plus 20, which is equal to 28 nanoseconds. That's the average access time in this case.